In our mission and vision, instilling excellence in electrical.
Hello, good day everyone. This is Professor Roger Flores of Central Mindanao University, Associate Professor 4 of the Department of Electrical Engineering and handling this subject EE41, Electrical Circuits 1. So today we are going to continue our discussion with Chapter 4. This is entitled Circuit Analysis Techniques and Network Theorems. Okay, this is the contents of our Chapter 8. So we have this Maxwell's Loop mesh method, the Superposition Theorem, the Noodle Method, the Tibinins Theorem, Norton's Theorem, delta to y or y to delta. Actually, this chapter here will discuss how you are going to simplify our circuits, our equations, so that we'll be able to determine the parameters that will be being asked and in the problem, no, in a simple or in the basic circuit analysis. Okay, so in other words, this chapter will discuss solutions on different circuit analysis, no. So these 6 topics or contents will help us to simplify or to give solutions to any electrical circuit problem. Okay, but before that, let us discuss first the standard signs and conventions. This is just conventionals, no? So as you can see here, we have this circuit. Okay, so this is the battery that give us, so that is the battery. They have the positive terminal. We have this negative terminal of that battery. No, if the loop enters the negative sign, okay, if the loop enters the negative sign and goes out on the plus sign, the battery or the electromotive force EMF is positive. If the loop enters the negative, the positive sign and goes out in negative sign, the battery is negative or the voltage is negative. So this is just anyway conventional, so that we will be able to analyze, so that we will understand each other to analyze the given circuit at the source side. No? So next, if the loop for this second circuit here, if the, okay, so we have here the circuit, no? So if the current will enter at the positive side, the current direction is from positive to negative, then the loop or the resistance voltage drop is negative. Okay, in the voltage drop, no? If the loop direction is opposite to the current direction, then the resistance voltage drop is positive. So that is our conventional direction or signs of our current and voltage. Okay, so let us formally start our discussion with this Maxwell's loop, or some of this Maxwell's loop. Some were called this one as mesh or mesh method. Okay, this Maxwell's mesh method involves a set of independent loop currents, and these currents are employed in connection with appropriate resistance when the Kirchhoff's voltage law equations are written. Okay, so just take note that the Maxwell's loop method will have its independent loop current. Okay, then we apply here the KVL, the Kirchhoff's voltage law, where we are going to sum up the voltages from the voltage source to voltage drops in the load, no? So as we can recall, that Kirchhoff's voltage laws said that the summation of all voltages, voltage rise and voltage drops, is equal to 0. Okay, so The arbitrarily assumed loop currents. So we have the as we mentioned that we have these independent loop currents, and they are that is arbitrarily uh, exist, no? May or may not exist in the various resistors, but when determined will readily yield the desired values by simple algebraic additions. Okay, simple algebraic additions. When we say algebraic addition, then it will do with respect to the positive negative algebra, no, solution. We have these steps used in this mesh method or loop method, no. So in solving a circuit using mesh, no. So we have number one, we have arbitrarily assigned a clockwise current to its interior loop in the network. Okay. So when we say loop, there is a continuous. There will be no open circuit. No, the current path is continuous. That's a loop. So try to assign a clockwise direction. No, clockwise direction for this independent loop current. Okay. Although the assigned current may be in any direction, a clockwise direction is used to make later work simpler, so that we will agree each other. Okay, number two, using the assigned loop currents indicate the voltage polarities, no? So across all resistors. So we have those if we have these resistors connected in the circuit, then assign the polarity for each resistor based on the loop current. Okay, so the arbitrary loop currents now inside the loop. The polarities of the voltage drop due to its loop current should be indicated in the appropriate side of the component. So the appropriate side of the component. So for example, if we have this circuit, if we have this loop current here, we have another loop current here, the terminal or the voltage terminal or polarity should be indicated for this loop here at the left side, then or the right side, no? So in my right, no? So we have to assign our polarity correctly. Okay. Number three, applying Kirchhoff's voltage law, write the loop equations for each loop in the network. Do not forget that resistors are common to loops with two voltage drops, one due to each loop. Okay. That is number three. Number four, solve the resultant simultaneous linear equations. No, resultant simultaneous linear equations. So apply now your algebra, determinants, or your matrix. Use any other solutions for the linear algebraic equation. Number five, steps. We have branch circuits are determined by algebraically combining the loop currents which are common to the branch. Okay, so combine all the loop currents which are common to each branch. Okay, so let us try this example number one here. So example number one, we have this find the current in each branch for the circuit of figure below. So as you can see here, let us study the let us study here the circuit or observe, no? So as you can see, you have your two loops here, loop number one, and we have this loop number two. For loop number one, we have this I1, and loop number two, we have this I2, no? So this is what we suggest for a solution, no? That assume a loop current clockwise directions. Okay, and when we say a loop, there is no open or open circuit here with these two loops, no? So as you can see here that we have these several voltage sources. We have A1, we have this A2, and we have this A3. And take note of the polarity of A1, A2, and A3, no? Again, just a reminder that for the polarity of or the polarity of our voltage source, we said that if it has longer horizontal bar then or vertical bar, basta yung bar natin is longer, then that is positive polarity, and yung shorter is yung negative polarity. So as you can see here, we have three resistances. We have R1, we have 2 ohms, R2, we have 2 ohms also, and we have this R3 is also R3 is 4 ohms. Because of this polarity of because of this loop current I1 and loop current I2, so we have this the polarity for the resistor or the load. We have this positive and we have this negative. We have for the R2 here, this is the positive and this is negative due to current I1, loop current I1. And due to loop current I2, we have this negative and we have this positive to make this voltage drop. So we have also for R3, due to loop current I sub 2, then we have this positive and we have this negative. Then take note where this I sub 2 enters in this voltage source 3. So it enters at the negative and out to positive. Okay. Our E1 is 6 volts, our E2 is 4 volts, and our E3 is 2 volts. Okay, so that is our observation. Okay, so for step 1, loop currents are assigned as shown. These currents are designated I sub 1, I sub 2. For step 2, voltage polarities are assigned according to the loop currents, as I mentioned a while ago, as we observed in the figure that we have. And notice that the resistor R sub 2. Okay, so we have this resistor I sub 2. You have this R sub 2. We have 2 ohms, and it has 2 different voltage polarities due to the different loop currents. Okay, so we have step number 3. The loop equations are written by applying Kirchhoff's voltage law in each of the loops. No? So in each of the loop, we have to create the loop currents using KVL, the Kirchhoff's voltage law. Then as you can see in loop 1 here, we will start at the voltage source of 6 volts A sub 1. Then voltage source of A sub 1. Then since this is positive to negative, this is minus here. Minus your resistance of 2 ohms times I1, the loop current I1. Then with respect to this polarity of positive to negative, due to loop current 1, then we have this minus. So we have again minus 2 times I sub 1. And then due to current I sub 2, with this resistor 2, okay, so this current will enter in this positive to negative. So that is why we have this positive 2 ohms times I sub 2. Then this I1 also enters, no? Because we are considering loop current 1. Our I1 will enter to positive and out to negative of this E sub 2 voltage source. So that is why this is minus. Okay, so this is minus 4 volts, and that is all in all equal to 0. That is Kirchhoff's voltage law using this loop 1. Now, let's proceed to this loop number 2. Okay, loop I sub 2 here. Then let's begin with this voltage source of E sub 2, the 4 volts. So this is from negative to positive. The current clockwise will enter to negative, out to positive. So that is why we have this 4 volts. Then we have our polarity here at this second loop here, positive to negative. That is why we have minus 2 ohms times I sub 2. Okay, plus we have this due to current I sub 1 in the second loop. So your current I sub 1 in the second loop will be clockwise, and it will enter to negative to positive. That is why we have this positive 2 I sub 1. Okay, so as we said, R sub 2 is reacted with, it will be reacted with 2 loop currents, I1 and I2. So with this second loop here, and with respect to loop current I1, then that is positive because I1 will enter here at negative out to positive in the second loop side here. So we have that positive 2 ohms, our resistance, times I sub 1. Then we have for another voltage or another resistance R sub 3 here, your loop current I sub 2 is entering positive terminal to negative. That is why we have this minus 4 I sub 2. 4 ohms I sub 2. Okay. Then pagdating natin dito sa loop current, the voltage source 3, then your loop current I sub 2 will enter in the negative terminal out here with the positive terminal. That is why we have these 2 ohms. Okay. So that is these are the equations that we were able to create using Kirchhoff's voltage law. Try to simplify the equation. We have here, to simplify the equation, reduce to collect like terms and reduce to the simplified equation. We have 4 ohms of times I sub 1 minus 2 ohms times I sub 2, and this is equal to 2 volts. Okay, that is equal to 6 minus 4, that is, you have this 2 volts. For this second equation, loop 2, okay, so your I1 here, if you're going to transpose, so we have this, add this one 4 volts and 6 volts, they are positive, so that's equal to 6 volts. So the other, this other terms here will be transposed to the other side. That is why your I1 here will become negative. So we have this negative 2 ohms I sub 1, and then we have this negative 2 and negative 4 with I sub 2, and then transpose to the other side, it will become positive 6 I sub times I sub 2. Okay, so that is the equation using Kirchhoff's voltage law of the second loop. Okay, so you can, as I mentioned a while ago, that you can use any of this solution, algebraic solution, but of course, I think it is more easier to use determinants. Okay, because this is a simultaneous equation. Okay, so if you can recall our determinant, then try to the denominator here are all coefficient of the equation 1 and equation 2. So okay, so we have this 4, the minus 2, then we have this minus 2 and 6. So if you're going to solve for I sub 1, then try to replace this first column with our constant. Our constant, as we said, that it is 2 and 6. So remain this second column. We have minus 2 and 6. So try to cross multiply. This is an application of determinants. So we have this 2 times 6 is plus 12 minus minus 6 times minus 2, that is positive 12. So that is equal to 24. So here, our denominator, you have 4 times 6, we have positive 24. And then this is minus 2 times minus 2, we have this minus or positive 4, so it is minus, so we have this minus 4. So if you're going to, we have this 24 minus 4, no? So if you're going to simplify, the numerator is 24 and the denominator is 20. So more or less, our loop current I sub 1, loop current, take note, this is a loop current. Your loop current I1 is equal to 1.2 amperes. So similar solution here, apply your determinants. Write back the first column because you are going to solve for I sub 2. Then write back the first column, you have 4 minus 2. And then your second column, because your I2 is your unknown, the second column here will be replaced by the constant of the equation, which is 2 and 6. So the same ang denominator natin. So we have to simplify this. We have this 24 plus 4, 4 times 6 minus 2 times 2, that is a positive 4. Then divide by 24 minus minus 2 times minus 2, that is minus 4. So more or less our denominator or our numerator is 28 and our denominator is 20. So I sub 2 now is our loop current 2 is equal to 1.4 amperes. So we are talking here loop current, no? Loop currents. So for the branch circuit, okay, just go back here. For your the branch circuit for R sub 2, and the current that will flow here at resistor 2 is we have the reaction between loop current 1 and loop current 2. So at this resistor 2, the direction of loop current 1 is clockwise, and the direction of current 2, loop current 2 is clockwise, but they will meet here at resistor 2 at opposite direction. Then you have to use algebraic solution. So that is why if we are going to assume that the direction, the loop current I sub 2 is 1.4, and with the loop current I sub 1 is 1.2, if you're going to sum up algebraically, then it will result to 0.2 amperes. So what is now the direction of our current in R sub 2? Because the loop current I sub 2 is greater than the loop current I sub 1. So therefore, the direction of the loop current I sub 2 will be followed, no? So pataas yung direction ng I sub 2 natin. So you have to choose the direction of the current at resistor 2. So ibig sabihin, ang actual direction ng current natin sa R sub 2 is upward, not downward. Because I sub 1 is 1.2 only and I sub 2 is 1.4. So follow the direction of I sub 2, which is at resistor 2, it is upward. Okay, so that is how you're going to determine the current in resistor 2, where the two loop currents will interact each other. Okay, so that is mesh or Maxwell's method. Now, to continue, let us discuss superposition theorem. And accordingly, it is in superposition theorem, this is applicable for several voltage sources also, no? In a network of resistors, the current in any resistor is equal to algebraic sum of the currents delivered by its independent sources. So take note that we will have an independent sources. It might be voltage sources or it might be a current source. Okay, so the current in any resistor is the current in any resistor is equal to the algebraic sum of the currents delivered by its independent sources using that its sources. Okay, its sources is acting alone or independent with respect to the others. The total current in any part of the linear circuit equals the algebraic sum of the currents produced by its sources. Okay, so remember this one for superposition theorem. If a source is operating alone, the other current sources are open-circuited, while the other voltage sources are short-circuited. So it is understood that whenever we have these two or more sources, take note that for the voltage sources, okay, you should have to use short circuit, no? Okay, so if you're going to consider the current sources, for example, if we have these two different types of sources, pag i-consider natin yung voltage sources, then ang gagawin natin doon sa current source, i-eliminate natin yan. So pag it is a current source, then you have to eliminate, then open circuit. Pero kung yung i-consider natin na voltahe ay voltahe na sources, no? So you have to remove that voltage source and replace it with a wire, then it will result to a short circuit source, no? So according to the theorem, the superposition theorem, okay, the total current through or voltage across a resistor or branch may be determined by summing up or summing the effects due to its individual or independent sources. So to apply superposition theorem, we have listed here some of these steps to simplify or apply superposition theorem. Number one, it is necessary to remove all sources other than one being examined. So we have, if the sources are, as I've said, more than two sources or one sources, then you have to analyze the circuit one by one based on individual source connected in the circuit. In order to zero a voltage source, we replace it with short circuit. Since the voltage across a short circuit is 0 volts. So in other words, if we have these voltage sources, then you have to replace it, no? I-short circuit natin yung battery or bulb voltage source. Pero yung if the source is current, then it will be zeroed out. And how to zero it out? Then you have to replace it with an open circuit. Okay, so that is how you're going to analyze individual source or sources, either voltage or current sources. Okay, let's consider this example number 2. We have this circuit diagram here. Okay, so as you can see, we have these two sources, the voltage source and we have the current source. Our voltage source is 20 volts and our current source is 2 amperes. Okay, so we have this fictitious load current, load resistance of 16 ohms, and then the resistance of this, we have here a resistance of 24 ohms. Okay, so the problem is to determine the current in the load resistance. We have this I sub L, and verify if superposition theorem that does not apply to power. So because actually superposition theorem will not apply the solution to power. Okay, so we have this for solution number 1. So we have to determine letter A. We first determine the current through R sub L. The current through R sub L due to the voltage sources. So this is what we are going to do. We have to independently solve for the load current using the voltage source here first. So we have to eliminate current source, no? So how you are going to eliminate current source? Then you have to remove, open circuit this current source here. Okay. So we have this. Okay, so we have this one, no? Open circuit na to. So we have to solve for I sub L. So as you can see, we have the code here or sub of 1, no, in parentheses, because this is the first solution. Analyzing the load current using the load voltage and source voltage only, removing the current source. Okay, this is our first solution. So as you can see here, if ganito na yung circuit natin, meron tayong voltage source, then nawala na yung current source natin. We have this resistance R sub 1, load resistance of 16 ohms. So ano nangyari sa resistance natin? It seems that they are connected now in series, no? So R1 and R sub L are connected in series. So to determine yung load current natin, okay, to determine yung load current, so anong gagawin natin? By Ohm's law, it is just load current is equal to the voltage. We have this voltage divided by the sum of these two resistances. So that is an application of Ohm's law. So that is why we have this I sub L1. Okay, so we have this 20 volts divided by our load resistance is 16 plus our R sub 1 is 24. So, as you can see, if you're going to simplify this one, then we have this current of 0.5 amperes. Okay, so that is if we are going to consider our voltage source and eliminate first the current source. Next thing that you're going to do is reanalyze again our circuit using this source current. Okay, so we have this source current, and we have to eliminate our voltage source. Then how to eliminate the voltage source? Replace the voltage source with a short circuit conductor. So that is why we have here it is short circuited here. No, voltage source replaced with a short circuit. So try to analyze now our new circuit. You have this resistance R sub 1, and you have the current source of 2 amperes. You have the load resistance of 16 ohms. What we need is to again compute the current I sub L, or the load current we have this parenthesis 2 here because this is our second solution, and this time we will be using our current source. Eliminated natin yung voltage source. Okay, so try to analyze our circuit now. With this current, with this source current, R1 and R sub L are now, these seems connected parallel. Okay, R1 and R sub L are connected now in parallel, considering our source current here of 2 amperes. Then as you can see, the direction of your current this is downward. Okay, that according to current divider, if this I source here of 2 amperes will now become, if you can still recall our current divider, it will now become our total current or source current in a way. So our total current is equal to, okay, so if you are going to solve I sub L here, so it is equal to the resistance at the opposite, so this is 24 ohms, divide by the sum of these two, and then multiplied the total current. Okay, the total current. Now your total current is 2 amperes. Now why is that this is negative? Okay, so why is that this is negative here? This is negative because your current is downward. That supposedly this current is upward, then it will be divided by I sub L here. Okay, and it will be divided by the current dito dadaan sa R sub 1. Okay, so that is why parehas lahat yung direction ng mga current, so including the source current, so that is why this will become negative. Okay, so what will be the result if you're going to simplify this? Then that is equal to minus 1.2 amperes. But anyway, don't worry by that sign minus, because it will just tell us the direction of the current. Okay, so what is now the resultant current? Therefore, we have two currents, I sub L1 and I sub L2. Okay, so I sub L1 is using voltage source, and I sub L2, that is the load current using the current source. Okay, so take note that okay, just go back here. Take note that our I sub L2 is negative 1.2, and our I sub L1 is 0.5 amperes. So try to simplify this one. 0.5 minus 1.2, then that is equal to minus 0.7 amperes. So that is our I sub L, the load current. Now take note, this is negative, so the actual direction of your current is the load current is opposite to what we assume. Now a while ago we assumed that the direction of our load current is downward, so therefore it is not downward. Okay, opposite naman yung polarity, yung sign niya, so it is now upward, not downward. Okay, consequently the current, the current through R sub L will in fact be upward with a magnitude of 0.7. So yun ang sinabi niya. If we assume incorrectly that the superposition theorem applies for power, So, ibig sabihin, inadvertently na-assume natin na, ma-apply daw ito sa power, then what is the formula of power? That is I squared R. So, we have this for the first solution of using the voltage source, then we have this P sub 1 is equal to I sub L1 squared R sub L. Or this is the formula of power, revised formula of the power, which is I squared times R. So the load current in the first solution is 0.5 quantity squared, then multiply it by your resistance, load resistance of 16. More or less, your P sub 1, or the first solution that we have, is approximately equal to 4.0 watts. Okay, so for the second solution, as we said, we are using the current source, and our result for our current is 1.2 quantity squared times the resistance of the load. More or less, that is 23.04. If you're going to sum up our power, so we have this P1 and P2. P1 is, as I've said, this is the power if you're going to use the, that is the power that we're going to use our source voltage, and P sub 2 is the power if you're going to use the current, no? So we have this 4 watts and 23. If you're going to add algebraically these two powers, P1 and P2, that it will yield to 27.04. Okay, so if you're going to have a different solution, then we said that our total current I sub L is 0.7. So 0.7 amperes squared times the resistance of 6 ohms, then your load power is only 7.84. Okay, so that is why we said that it is the power is the solution of power here is not applicable for the superposition theorem, because if you're going to sum up these two powers, it will yield 27.04 watts. But actually the correct solution here is only 7.84 watts. Okay, so that is our solution for example number 1. Okay, next we have this Noodle method, or example number 2, I'm sorry. We have this Noodle method. This Noodle method is another procedure of our circuit analysis, where every junction in the network that represents a connection of 3 or more branches is regarded as a node. Okay, so it's clear that it must have a node and it must have a connection of 3 or more branches. Pero yung kung dalawa lang yun, hindi natin ma-apply yung nodal method. Okay, so moreover, considering one of the nodes as a reference or zero potential point, current equations junction or current equations are then written for the remaining junctions. Thus, a solution is possible with n-1 equations, where n is the number of nodes. Okay, so consider this illustration here. As you can see, we have two voltage sources. We have this A sub 1, you have this A sub 2, meron tayong A sub 1 dito, we have A sub 2. We have several resistances. We have this R1, we have R2, R3, R4, and R5. So based on that circuit diagram, then we will have, let us identify nodes. And according to the definition of a node, mayroon tayong dapat 3 or more. No, 3 or more branch circuits. So as you can see here at node A, we have mayroon tayong branch circuits for R sub 1, mayroon tayong branch circuits R sub 2, we have branch circuits R sub 3. Okay, so this will qualify as a node, node A. Then for node B, we have these branch circuits R3, branch circuits R4, then branch circuits R5. Okay, so it will qualify to what we said as node B. So what will happen here below? So this is also a node, and this reduced to one node because this is a zero potential node, no? So this is a reference. So even though we have 4 connections, but you can reduce it into 3 nodes. Okay, so we have this one. no? I-combine lang natin lahat dito. Magiging reference or zero potential node po 'yan. Okay, so let us try to analyze the circuit and apply Kirchhoff's voltage law and Kirchhoff's current law. Okay, so first, let us apply Kirchhoff's current law at node A. So ano bang mangyari dito sa load A, sa node A? So let us analyze Kirchhoff's current law. And just to recap, Kirchhoff's current law is the summation of currents in a junction, entering and out, no? So the summation of this current is equal to 0. Okay, in a junction, no? So in other words, ito yung circuit natin, yung sa circuit natin dito, we have I sub 1 entering to node A, considering node A as our node, and we have this I sub 3 leaving that node A, and we have I sub 1 that is also leaving at node A. So therefore, we have that circuit equation of I sub 1 is equal to I sub 2 plus I sub 3. No? So makita natin, I sub 2 plus I sub 3, this is equal to I sub 1. Okay. So if you're going to consider voltage equation for each of these current in the Kirchhoff's current law, for I sub 1, anong gagawin natin sa I sub 1? No? Now, take note, this is your I sub 1. So, your I sub 1 is equal to the voltage is sub 1, yung sinimulan niya, doon siya nagsimula. And then, we have this I sub 2, no? So, therefore, your I sub 1 is equal to I sub 2 plus I sub 3. Yun po yung Kirchhoff's current law niya. I sub 1 is equal to I sub 2 plus I sub 3. Okay. What will happen here in our node B? So, yun po. Mayroon din tayong dalawang entering to node B. So, that is I sub 3 and I sub 5. And then, just consider I sub 4 here downward, and isa lang po yung direction niya, o yung direction niya downward. So, we can say that dalawa yung pupunta sa node B, and isa lang yung umalis sa node B. So that is why we have this I sub 4 is equal to I sub 3 plus I sub 5. Okay, so we have this equation here. Okay, so we have this for I sub 1, A sub 1 minus B sub A times R sub 1. What will happen to our I sub 2? Your I sub 2 here is ano ba nangyari natin? I sub 2 is now equal to I sub 1 minus I sub 3. Okay? So, ito nang nangyari ngayon. So, we have this B sub A minus B sub B divided by R sub 3. Okay, balikan lang natin ng konti. We have here, no? So, I sub the voltage here, no? You have this voltage B sub A minus voltage B sub B divided by R sub 3. So, collect like terms, B sub A, so that is equal to B sub A is equal to 1 over R sub 1. B sub, and we have this 1 over R sub 2 plus R over R sub 3. Then, separate natin itong I sub 3 and then resistor 1, no? Minus B sub B, R sub 3. Okay, so at node B, we can also apply the Kirchhoff's current law at node B. So, balikan lang natin yung circuit natin andito sa node B, no? So, entering yung I sub 3 at saka yung I sub 5, leaving yung I sub 4. So, ganito mangyayari. We have this I sub 4 is equal to I sub 3 plus I sub 5. Yung umaalis na kuryente. So, what is now our I sub 4? Our I sub 4 is equal to, this is your I sub 4. Your I sub 4 according to Ohm's law, this is the voltage. I sub 4 is the voltage over resistance 4. Okay? So, in short, we have this B sub B over R sub 4. Now, our I sub 3 is, we have this I sub 3 here. So, we have this equation, voltage B sub A minus voltage B sub B here. And then, divide by resistance R sub 3. So, ganito po nangyari niya. So, what we did here is you have to collect like terms or, common of V sub A minus E sub 1 over R sub 1. Then we have this minus V sub B divided by R sub 3. Okay, equal to 0. That is Kirchhoff's current law, no? So that is, we just simplify that one. For, go back here, no? For Kirchhoff's current law at node B, we have this I sub 4 is equal to I sub 3 plus I sub 5. Your I sub 4 is voltage V sub B over R sub 4, that is Ohm's law. Then our R3 is equal to V sub A minus V sub B divided by R sub 3. And then we have this what do you call this one? Our KCL at the last portion of our circuit. We have this A sub 2 minus B sub B divided by R sub 5. So collect like terms, simplify, and then we have this equation here. Okay, let us apply this example number 3. Apply nodal analysis to the network of the figure below. So as you can see here, we have again two sources. We have the voltage source and the current source. Your voltage source 24 volts, your internal resistance 6 ohms. Then the load resistance of R sub 2 is 12 ohms. Okay, so we have the source current of 1 ampere. So we have this one. So step 1 and step 2, network has two nodes. Okay, we have this node nga binigyan natin ng pangalan na V sub 1, and we have this zero potential nodes. Okay, the lower node is defined as the reference node at ground potential, and the other node is or as V sub 1. Okay, the voltage source 1 at this node 1. The voltage from node 1 to ground. Okay. So, step number 3, we have I sub 1 and I sub 2 are defined as leaving the node in figure below, and Kirchhoff's current law is applied as follows. Okay, so pababa yung I sub 2 natin. Okay, it will pass by at R sub 1. Then we have the resistance, internal resistance 6 ohms, and the internal or the source current is equal to 1 ampere. So, the current I sub 2 is related to nodal method B sub 1 by Ohm's law. So, we have this I sub 2 is the load voltage at resistor 2 of 12 volts. Then we have divide by R sub 2. But it is also equal to the other side, no? We have this another equal solution. Then that is equal to V sub 1 divided by R sub 1. Okay, so that is how you implement the example, or we have this equation. Now, accordingly, the current in I1 is also determined by Ohm's law as follows. We have this I sub 1 is equal to V sub R1, the internal or the resistance of the voltage source 1, and then the current source 1 of R sub 1. So, try to specify again, and then we will be able to arrive with V sub R is equal to V sub 1 minus E. V sub R is equal to V sub 1 and E. Okay, so next, we have this substituting the into the Kirchhoff's current law of that equation. Okay, so ano bang nangyari dito? We have this equation here. So, i-substitute natin ang ating equation. We have this I sub 1 plus I sub 2. Then we have this V sub 1 minus E over R sub 1. Plus the quantity V sub 1 over R sub 2. Okay, so simplify, arrange. So, we will be able to supply, we have our new equation of V sub 1. That is equal to I sub R1 plus I sub R2. Then we have this E over R1 plus 1. Okay, so try to simplify, no? Substituting numerical solution, so we v sub 1 over 1 6, then we have this 1 over 120, and then that is equal to 24 over 6, or 1.4, 1.4. So we have this, simplify this, we have this v sub 1 is equal to 1 over 4 pi divided by 4 pi, so we have this 5 amperes. Then we have also this current, voltage, and our voltage is equal to, or voltage v sub 1 is 1 over resistor resistor 4 ohms, then we have this 5 amperes. Then we have this v sub 1, 20 volts. So currents I1 and I2 can then be determined using the preceding equations. So we have this equation, I sub 1 is equal to v sub 1 minus E times R sub 1. We have 20 volts minus 24 volts is 6 ohms. Then you have to simplify that one, and it resulted to negative 0.667. So the minus indicates simply that the current I1 has a direction opposite to the opposite to that appearing in the figure above. So this is now our equation of I sub 2, that is equal to the load voltage of 1, then divide by load resistance R sub 2. So with this solution, we have this 20 divided by 12, or 1.6667. So let's continue our discussion with this Tibinins Theorem. So Tibinins Theorem here, just to give you a, what do you call this one? Mayroon tayong medyo talambuhay natin dito ni Leon Charles Tibinin, no? So, Tibinins Theorem here was formulated by Leon Charles Tibinins, no? So we have here Leon Charles Tibinin, and then he is an active in the study and design of telegraphic systems, including underground transmission, cylindrical condensers, capacitors, and electromagnetism. Okay, he is best known for a theorem first presented in the French Journal of Physics, Theory and Applications in 1883. So it occurs under the heading of Nouveau Theorem de Electricity Dynamique. Okay, in a new theorem of dynamic electricity, and okay, so that is the meaning of that French word, no? So and was originally referred to as the equivalent generator theorem. Okay, so we have also this. There is some evidence that a similar theorem was introduced by Hermann von Helmholtz, in 1853. However, Professor Helmholtz applied the theorem to animal physiology and not to communication or generator system. Okay, and therefore, he has not received the credit in his field that he might deserve. That supposedly the credit supposedly yun may bigay sana yun kay Helmholtz, no? Pero hindi nabigay sa kanya because this theory is applied only to the animal physiology. Okay, in the early 1920s, AT&T did some pioneering work and using the equivalent circuit that may have initiated the reference to the theorem as simply Tibinins Theorem. Okay, in fact, Edward Norton, the engineer at AT&T at the time, introduced also a current source equivalent of the Tibinins equivalent, currently referred to as the Norton's equivalent circuit. So, okay, so as an aside commandant, Tibinin was an avid skier and in fact was commissioner of an international ski competition in Chamonix, France in 1912. So that is just a simple parang bibliography of Leon Charles Tibinin. Okay, you have here. So now to discuss more about Tibinins Theorem, sabi po niya dito, any two-terminal linear bilateral DC network can be replaced by an equivalent circuit consisting of a voltage source and a series resistor. Okay, yun. Kung kahit gaano ka complicated or complex yung circuit natin, pwede natin yung internal circuit natin, pwede natin ma-combined and it will be represented by single voltage source and the single resistance. Tinatawag natin yung voltage source na yan, Thevenin voltage, and yung resistance is Thevenin resistance. Okay. So, Tibinin Theorem also combined in any combined of batteries and resistance with two terminals can be replaced by a single voltage source V sub TH or E sub TH and a single series resistor of R sub TH. So, yun ang sabi natin kanina. So, the value of V sub TH is the open circuit voltage at the terminals, no? And the value of the Thevenin resistance is the Thevenin voltage divided by the current with the terminals short-circuited. Okay. So, in other words, to solve for the Thevenin voltage, i-open circuit natin yung dalawang terminal, the load terminal, then tsaka i-compute natin kung ano ang voltahe doon sa open circuited voltage terminal, terminal nga, sa dalawang terminal. So, pag if you're going to compute for the resistance, then it will become the voltage, the Tibinin voltage divided by the current. No, that is the short circuit current. So, yun ang problema natin. Paano ba natin paano ba natin pag-solve ng short circuit current? It's just simple. Short circuit yung dalawang terminal natin. Pag voltahe yung kukunin natin, Thevenin voltage, i-open circuit natin yan. Pero kung kuha tayo ng open circuit, yung sa current, yung current, then gawin nating short circuit ang ating dalawang terminals. Okay? So, we have here solution number 1. So we have this calculate dalawang solution natin, no? Dalawang solution natin. So calculate the output voltage V sub EV. So yun ang output or terminal voltage natin sa load terminal V sub EV when in open circuit condition. So open circuit condition, no load resistor, meaning independent resistance. This is your V sub TH or terminal or your Tibinin voltage. Number 2, calculate the output current of I sub EV, yung terminal current with this or those leads are short-circuited. Okay. Then our load resistance now is 0 because it seems that our load is short-circuited. So we will be able to solve for the load Thevenin resistance, which is equal to the Thevenin voltage divided by the Thevenin current. Okay, so that is your solution. Okay, so we have also solution number 2. So we have this solution number 2, letter A. Now replace voltage sources with short circuits and current sources with open circuits. So yun, na-lecture natin yan kanina. So anong gagawin natin so that we'll be able to determine the looking back resistance we have here, the Thevenin resistance, paano yan i-compute. So yung mga voltage source natin, lagyan natin ng conductor na magiging short circuit yan. Ang ating current source will be just open circuited. Kunin lang natin na yung current source natin tsaka magiging open circuit na yan. Then try to analyze the circuit and solve for the resistance based on the load terminal, not based on the source but based on the load terminal. Okay, so the equivalent circuit is a voltage source with voltage V sub TH in series with a Thevenin resistance R sub TH. Okay, so yun nga ang mangyayari natin ngayon. Okay, so we have this example number 4. Okay, determine the Thevenin equivalent circuit external to the resistor R sub L. For the circuit figure below, use the Thevenin equivalent circuit to facilitate the current the current through R sub L. Okay. So as you can see, we have these two. This is similar to our example a while ago. We have these two sources, the voltage source and the current source. So again, what you're going to do here first, solve for the ang solution natin step number 1. Okay, so open circuit, no? So you have this open circuit. You have open the load terminals. So ano bang mangyari dito pag ma-open natin itong load terminals? So we have only these solutions here or circuit here. We have E, R1, and we have this I1. So we have these two sources. So to solve for the looking back resistance of R sub TH here. So paano ba natin siya to determine? So as we said, ay kunin natin yung voltage source saka yung current source. How to do it? Then replace the voltage source with a conductor, and sa current po natin kunin natin yung current source, so it will become open circuit. So if you're going to determine the looking back resistance or the Tibinin resistance at the terminal side A and B, now as you can see here, this is just equal to R sub 1. Wala na tayong ibang resistances or resistance, then yung R sub TH natin is also R sub 1, or that is 24 ohms. Okay, so the Thevenin resistance between the terminal is looking back resistance R sub TH, that is equal to 24 ohms. And then for step number 4, this is from the figure above, the open circuit voltage between the terminals A and B is found to be, your B sub EB is equal to 20 volts minus the voltage drop at resistor, the R sub, the Thevenin resistor, or the internal resistance. Okay? So, balikan na natin na. Okay, as you can see here, no? So, okay, so balikan na natin ng konti dito. So, okay, so what you're going to do to solve for the voltage here, is short circuit lang po natin ito. So we have this they have the source voltage 20 minus the voltage drop here. So ano po ba yung voltage drop natin dito? That is 24 times your current. This is the current that will flow here. So 24 times the current of 2 amperes, we have this 20 volts. Okay. So this is 20 minus 24 ohms times 2 amperes, then we have this minus 28 volts. Okay, so that is your terminal, that is your Tibinin voltage. So 28. So take note of the connection of the Tibinin voltage. Why is that negative tong dito sa taas, positive dito sa baba? Because our according to step number 4 here, this voltage that we will be able to derive is minus 28. So baligtad yan. So we have this minus. So if you are going to consider clockwise direction, then the loop current enters here at the positive side to negative. So that is why we have this baligtad. This will become negative, no? Negative voltage it is of TH. Okay, so we have this the Tibinin resistance, the looking back resistance, as we mentioned a while ago for our solution. We don't have any other resistances, so we will use this R sub TH equal to 24. So you have the resulting Tibinin equivalent circuit is this one. Then you have the load resistance of 16 ohms. Okay, so therefore, if you're going to solve for the load current, so we have the load current is using Ohm's law. The voltage of 28 divide by the sum of these two, the 24 and 16 ohms. So that is more or less equal to 0.7 amperes for the load current. Okay, so we have this solution here of example. Then let's proceed to Norton's theorem. So according to the bibliography of Tibinins Theorem, also Norton created its own analysis in terms of the current. Gumawa siya ng kanyang his own theorem. Okay, so this Norton theorem states that any two terminal linear bilateral DC network can be replaced by an equivalent circuit consisting of current source and a parallel resistor. Okay, so yung ginagawa ni Thevenin kanina na gumamit siya ng Thevenin voltage, yung resistance niya, yung Thevenin Thevenin resistance is in series ng yung source na Thevenin voltage source. But ngayon, our current here, according to Norton, ay parallel siya doon sa looking back resistance R sub N. So that is Norton's theorem. Okay. So we have several steps to simplify or to simplify our circuit. Number one, we have removed that portion of the network across which the Norton equivalent circuit is found. Mark the terminals of the remaining two-terminal network. Okay, so calculate the Norton resistance by first setting all resources to 0. So voltage sources and current sources, set that those sources into 0. So paano maging 0 yung sources natin? So voltage sources replace with a short circuit conductor. Current sources i-open circuit natin yung source natin. So kunin lang natin, tanggalin natin yan. Yun na nga po. And then finding the resultant resistance between the two marked terminals, and it will become your looking back resistance, Norton resistance, R sub N. Okay, so for the step number 4, if the internal resistance of the voltage and or current sources is included in the original network, it must remain then when the sources are set to 0. Your Norton resistance is also equal to the Tibinin resistance. So paano gawin yun? So balik tayo sa kung paano kinuha ni Tibinin yung looking back resistance. Yun din ang gagawin natin kay Norton, no? Yung looking back resistance gagawin, it is equal to the Norton resistance. Okay. So wala tayong problema sa pag-solve ng looking back resistance R sub N or R sub TH. They are just the same. So for steps number 5, calculate I sub N, the Norton current, by first returning all resources to their original position and then finding the short circuit current between the marked terminals, and it is the same current that would be measured by an ammeter placed between the marked terminals. Okay, so balik natin yung mga sources natin. Pag mayroon tayong voltage source o current source, balik natin. Tsaka i-short circuit natin yung load terminal, and then try to determine the current. And that is your, what to call this one, Norton current. Okay, so for step number 6, draw the Norton equivalent circuit. The portion of the circuit previously removed, replaced between the terminals of the equivalent circuit. So ito nang nangyari sa atin ngayon. This is the circuit for the Thevenin, na mayroon tayong Thevenin voltage, mayroon tayong Thevenin resistance or the looking back resistance. Now for the Norton, we have this current source, and the current source here, I sub N, it is just simply equal to the Thevenin voltage divided by the Thevenin resistance. And ang Norton resistance natin magiging parallel on the current source. Okay. So anyway, your R sub N, your Norton resistance is just the same with the Thevenin resistance. Okay, so let us analyze this example number 5. find the Norton equivalent circuit for the network in the shaded area of figure below. Okay, so this is the shaded area here. Okay, ito po. So, mayroon tayong voltage source of 9 volts. Mayroon tayong R sub 1 which is 3 ohms. Mayroon tayong R sub 2 which is 6 ohms. So, by the way, hindi lahat na problem is ganito kasimple lang ha. So, baka mayroon pa tayong mga complicated circuits. And try to apply those different methods to simplify our circuits here. Okay, so you have the load resistance of R sub L at terminal A and B. Okay, so find the Norton equivalent circuit of the network in the shaded area of figure below. Okay, so let us have these solutions. So, ang gawin lang natin muna, itanggalin natin yung load natin at terminal A and B. So, kung titignan natin na yung step number 3 natin, no, shown in figure below, and ano mangyayari dito if you are going to compute your Norton resistance. As I've said, your Norton resistance is similar to your Tibinin resistance, and that we are going to determine the total resistance at this within this terminal A and B. So this will become the looking back resistance. So if we have this voltage source here, then anong gagawin natin na voltage source natin to determine the looking back resistance is short circuit lang po natin. So anong mangyari na dito ngayon? So your R sub 1 is now in parallel with R sub 2. So that is why your R sub n, the Norton resistance or the looking back resistance, R sub n is now equal to the parallel combination of 3 ohms and 6 ohms. So to simplify or compute R sub n, the looking back resistance, the Norton resistance, as I've said, which will be equal to the Tibinin resistance, is equal to 3 times 6 divided by 3 plus 6. That is the formula to solve for the parallel resistances. So, if you're going to simplify this, it will yield to 2 ohms. So, mayroon tayong 2 ohms diyan for sa Norton resistance natin. Okay. So, to determine our Norton, mayroon tayong Norton resistance, kunin na naman natin yung current, Norton current. No? Paano ba yan mag-determine ng Norton currents? It is just simple. Short circuit yung terminal natin. Pag i-short circuit natin itong terminal na A and B, and then ano mangyari dito sa resistor 2, it will be also short circuited. So, kaya nga nilagyan natin ng short circuited itong R sub 2. Kasi wala na, tingnan natin dito. Short circuited naman ito eh. So, maging short circuited naman ito. So, ano bang mangyari sa I sub n natin? Ito, ganito. I sub n din na itong yung kakurente natin dito. So, yun nga. Pag ma-short circuit na ito, yung current natin is equal to 0. So, our solution now will be reduced to solve for I sub n, no? Pag short circuit natin ito, short circuit na rin ito. So your I sub n is equal to the voltage divided by the resistance. That is according to Ohm's law. So we have this V sub 2 is equal to I sub 2 times R sub 2 according to Ohm's law. So I sub 2 is equal to 0 because na short circuit na po yan. So we have this R sub 2 which is equal to 6 ohms. So more or less, B sub 2 is equal to 0 volts. Now, if it is 0 volts, then we can say that I sub n is equal to the voltage divided by the resistance of resistor 1. So we have this, the voltage of 9 volts divided by the resistance of R sub 1, which is equal to 3 ohms, then it will results to I sub n is equal to 3 amperes. Okay. So, anong nangyari dito? So, we try to convert, no? So, this circuit is the same as the first one considered in the development of this Tibinins Theorem. A simple conversion indicates that the Thevenin circuits are in fact the same. Okay, so we have this one. This is our Norton. Okay, so we have this our Tibinin circuit. So, yun na po. Yun ang conversion ng Thevenin to current or Norton or vice versa. Okay. So, do you have as we continue here, mayroon tayong maybe this is our last topic. We have y to delta or delta to y transformation. Okay, so accordingly, the transformation is used to establish equivalence for networks with three terminals, where these three elements terminate at one point node and none is a source. The node is eliminated by transforming the impedances. Okay, so that is the conversion of delta to y or y to delta. Okay, so let us start. Okay, by the way, the y to delta transform or transformation, also written y or delta or y delta, no? So we have this one. Kenneally's delta star transformation is star Maze transformation, or just simply T to pi, no? Transform is a mathematical technique to simplify analysis of electrical network. Okay. The name derives, by the way, the name derives from the shapes of the circuit diagrams, okay, which look respectively like letter Y and letter Greek capital letter delta. So how you're going to simplify the delta to Y transformation, or how you're going to transform the delta connected resistance to Y connected resistance, okay? So, by the way, later on, we will try to solve problems related to this, no? But this is just realistic that there will be some time that our resistors are connected in delta, and there will be some time that our resistances are connected in Y. So, this is something like Y, okay? So, we have this, no? If we have this delta to y, if you're going to convert or transform delta to y, okay, so we have this one. So as you can see in the figure, we have this delta, and it is labeled r sub a, r sub b, and r sub c. We have also this y, and it is labeled r sub 1, r sub 2, and r sub 3. Okay, so to determine any of this converted y, we have to determine, for example, R1, R2, and R sub 3. So we have this analysis. Your R sub y, where this is your resistance connected in y, is equal to the resistance delta adjacent to 1. Okay? So, adjacent, no? Delta adjacent 1, or delta resistance adjacent to 2. Okay, adjacent 1. Okay, kung ito po yung delta natin. So we have this is adjacent, no? This one and this one. Okay, so ito ang adjacent. So if we're going to determine this y here, so ito po i-multiply natin itong dalawang adjacent, and then i-add natin yung the denominator is the sum of these three sides resistance. Okay, so that is why we have this for R1, R sub 1 is equal to the product of R sub A and R sub B. Okay, dito po yung R sub 1 natin. So yung adjacent niya is R sub A times R sub B. Then divide by the sum of these three. You have RA, R sub B, and R sub C. So we have this on R sub 1. So for example, R sub 2, what is R sub 2 now? So R sub 2, according to the delta to y transformation, R sub 2 is the product of these two here, R sub B and R sub C, divided by the sum of these three resistors connected delta. Okay, so how about R sub 3? Andito sa taas. Okay, dito po siya sa taas, no? R sub 3, it is just equal to the product of R sub A and R sub C Ito po yung nag-adjacent sa R sub 3. So, R sub A and R sub C. And then, divide by the sum of these three resistors connected now in delta. Okay? So, we have this R sub 3 is equal to RA plus, times R sub C, divided by RA plus R sub B plus R sub C. Now, what if there is a circuit having a delta connection, and then this delta connected resistances, now the three delta connected resistances are are equal. Okay, so pag mayroon silang the same amount of the resistance, so what you're going to do, you have this formula. The delta resistance, the total resistance in delta, or any current in delta, is equal to 3 times Ry, R sub Y in Y, no? So ito lang gagawin natin, yung delta natin is equal to 3 times the resistance Y. Okay, so we have this example. Find the equivalent Y circuit for the delta circuit shown in figure below. So we have this delta, and you are going to convert this into its equivalent Y circuit. So our delta here, the resistance between A and B, terminal A and B, is 30 ohms. Between B and C is 90. Between C and A is 60 ohms. So we have here the expected Y resistances, Y connected resistances. So we have this R sub 1. Okay, so just to give you an idea how to solve for R sub 1, this is just the product of this one here and the other side. So product of 30 times 60, that is R sub 1, divided by the sum of these three. So 30 plus 60 plus 90. Okay, so that is your R sub 1. Simplify, more or less your R sub 1 is equal to 10 ohms. Okay, so to proceed to solve for R sub 2, so we have this R sub 2. Nasaan ba yung R sub 2 natin? Andito. So we have this at connecting terminal B. So how to determine R sub 2? Okay, just simple. Just multiply your 30 and 90. So we have this 30 and 90 divided by the sum of these three. So we have this 30 times 90 all over 90 90 ohms plus 60 ohms plus 90 30 ohms plus 60 ohms and 90 ohms. More or less your R sub 2 is equal to 12 ohms. So for R sub 3, nasaan na ba yung R sub 3? Dito sa kabila, sa right side. So your R sub 3 is just simply equal to the product of the adjacent sides. So we have 90 and 60 ohms, and then divide by the sum of these three. Now 90 plus 60 plus 30 ohms. So more or less your R sub 3 is equal to 30 amperes. Sorry, 30 ohms. It is equal to 30 ohms. So next we have this Y to delta. Okay, so we have this from the circuit given in Y, then transform it to delta. So we have this one, no? Our Y here is having R1, R2, and R3. Your delta here is having A, B, and C, respectively, for the delta connection. Okay, so according to the formula to determine the resistance of the delta connected or the Y connected load, it is the summation of the product of Ry sub I times R I or Y times J, all pairs. So pares-pares po yon. Divide by the opposite resistance. Okay, so ganito lang kadali yon. We have these three resistors connected in Y, R1, R2, and R3. So pares-pares lang natin yan, no? Product of R1 times R2 plus product of R2 times R sub 3 plus R sub 3 times R sub 1. So that is the numerator. Now to solve for the denominator, that is where the opposite side of your resistance nga kukunan natin ng transformation ng Y to delta. Halimbawa, andito. So we have this to solve for A, andito yung R sub A. So we have this the product of itong pares-pares nila. So R sub 1 times R sub 2, R sub 2 times R sub 3, R sub 3 times R sub 1. Divide po yan sa opposite side. So ano po ba yung opposite side ng R sub A? Andito po yung R sub A natin. Yung opposite side niya is R sub 2. So that is why we have this R sub 2. Okay? So R sub B. So we have to determine this R sub B here. Similar solution. The same ang solution natin ng yung numerator natin, pero yung denominator natin is yung opposite resistance. So we have this R sub this one is R sub B is equal to product or the sum of the products of R1, R2, R2, R3, and R3 and R1. But our denominator here is R sub 3. Okay, so for R sub C, hindi ito, sa opposite side po. So we have this, we have to combine this one pair by pair and then divide by the opposite of R sub C, which is equal to R sub 1. So more or less, ito po yung solusyon natin kung mag-transform tayo ng Y to delta. Okay, so to continue, we have this problem. Find the delta network equivalent of the Y network shown in figure below. So, in dito yung Y, at saka yung dito yung delta, which is your unknown. R sub A, yung opposite ng letter A. R sub B is yung opposite ng letter B. And R sub C, yung opposite ng R sub C. So, with this given, our given is for R1 is equal to 2.4, R2 is equal to 3.6, and R3 is equal to 4.8. Okay, so use your hand and your mind. So, to solve for R sub A in this given example here, okay, to solve for R sub A to this given example, tingnan na natin. Ano bang nangyari dito sa problema? Okay, so your R sub A is just the opposite of your resistor or R.8. So your R sub A is equal to the product of this R sub A 4.8 times 2.4 plus 4.8 times 3.6 plus 24 and dito po 2.4 times 3.6. Okay, so more or less R sub A is equal to 7.8. Similar solution, R sub B. Okay, so it is the product of R and dito sa numerator, and then this one, the product of these two resistors, and then the denominator is since this is R sub B, yung opposite po yung denominator. So, ano po ba yung opposite? That is po 3.86. Okay, so we have this solution here. You have this R sub A, R sub B, and R sub C. This is our answer. Now, another example. Example number 8. Find the total resistance of the network of figure below. Your resistance R sub A here, and dito po sa may dito sa kabila at terminal B and C. We have 3 ohms. R sub B, we have 3 ohms. And R sub C, we have 6 ohms. Take note that parehas yung R sub B at saka R sub A. But different yung R sub C. Okay? So, ang solusyon natin, gawin natin itong delta, itong shaded area. So, similar to this representation here. Gawa natin ng solution by using that somewhat the delta in the problem that we have. Okay, so convert this delta into its equivalent Y. And ganito yung nangyari kanina. So convert this delta to Y. So more or less R sub 1 is 1.5, R sub 2 is equal to 1.5 also. It is expected because our R sub B is 3 and our R sub 4 is 3 ohms. So, expected na mayroon din tayong dalawang equal sa R1 at saka yung R2 natin. So, ginagamitan natin ng delta to Y solution. So, by the way, mayroong mali dito, no? So, hindi po ito R2, but rather this is R3. So, this R3 is RA, RB over RA plus RB plus RC. Okay, so more or less that is equal to 0.75 ohms. We have already the equivalent Y resistance. So, what will happen? Your R1 is in series with 4 ohms here. Your R2, which is 1.5 ohms, will be in series with 2 ohms here. So, again, we will be able to simplify this circuit. Simplify. Okay, sum up this one, sum up this, then dalawa itong A and B magiging parallel resistance, then kunan mo ng parallel analysis, then you have to add it with the R sub 3 because your R sub 3 is also R sub 3 is having 0.75 and they are connected in series of this parallel combination of these two resistances. Okay, so our total resistance is now equal to 2.889. So that is how simply to determine the total resistance, even though it will look like we have no more other solution, but you can see here it is more easier. So convert this one to delta, and then gawin mo to ng y, and then itong branch na ito R sub 2 will be added to 2 ohms, yung branch na ito R sub 1 will be added to 4 ohms. Then this 2 will become parallel and in series with R sub 3. Okay, so more or less we finished our discussion in this chapter, and I hope that you will be able to understand our discussion here, in which this chapter will just help us to simplify our circuit. This is by using loop method or mesh method. We have the nodal method, we have the Tibinins Theorem, we have the Norton's Theorem, the delta to y transformation, and the other one. Okay, so if you believe that you learn some things of this discussion that we have, please subscribe to my YouTube channel, and then so that you will be notified whenever I have additional video discussion for the subject EE 41, which is Electrical Circuits 1, and this is our chapter 8. Thank you very much. God bless. Amping, and God bless you more.
We are one in eye mission and vision.